right, we're covering a lot of material, so we're running a little short on time. So I'm going to take both the cases for line integrals, and we're actually going to do them for the same problem. So here's an example where I've been asked to compute for sum f equal to 2xy I hat plus x squared j hat. I want to find the line integral along this parameterized curve I've been given. And so in more complicated problems, maybe somebody wouldn't give you the curve, you would have to find it. But for this one, we're going to have this curve given. And first, we're going to do this the easy way. So we're going to do this step A way. I'm going to say this vector field looks conservative. You can check the curl if you're not sure. But I'm going to go ahead and just try to find the potential function. And this is something that we covered in section 13.1, so I'm going to go through the steps kind of quickly. But I know that that should be derivative with respect to x in the I component, derivative with respect to y in the j component. So I know that my function f should be given by the integral 2xy with respect to x, which would give me x squared y plus some unknown constant that depends on y. And I know that it should be given by the second component integrated with respect to y, which would again give me x squared y, but now with some unknown constant with respect to x. Since I can see that I haven't created any extra terms, those unknown constants actually don't exist, and my function is just f equal to x squared y. And if I computed the gradient, I could go ahead and check that grad f does equal that vector field. And now I just need to know the endpoints. So if t equals 0, then x is equal to t squared is 0. Y is equal to 2t is equal to 0. And z is equal to t is equal to 0. So that endpoint has 0, 0, 0. Okay, and then at t equal to 1, I'm going to get x is equal to t squared is equal to 1. Y is equal to 2t is equal to 2. And z is equal to t is equal to 1. So I'm actually going to, oh no, that's such a big eraser. I'm actually going to put my points over here. So my first point was 0, 0, 0, and my second one is 1, 2, 1. Sometimes you'll just be given the endpoints and you don't have to mess with this part. But for my parameterization that I was given, I can go ahead and compute the endpoints. If somebody handed them to you, skip this step. But I can use the fundamental theorem. The integral of the vector field f over the curve c is just f at the endpoint, 1, 2, I think, minus f at the initial point. And there is a z component for both these things, but my vector field actually doesn't depend on z or have a z component, so it ends up not mattering. And so this is going to be for f equal to x squared y I'm going to have 1 squared times 2 minus 0 squared times 0. So that's just 2. But if I didn't recognize that, then I could have gone ahead and kind of plugged through this whole thing using parameterization, and we're going to find that we get the same answer. So my f is equal to 2xy I hat plus x squared j hat. And somebody told me that x is t squared, y is 2t, z is t, I think. All right, so I can go ahead and plug in that f equal to 2xy I hat plus x squared j hat should actually be equal to 2 times t squared for x times 2t for y I hat plus t squared squared for x squared j hat. So that's going to be 4t cubed t to the 4th. And if I want to have the k component, it's just a 0. And our parameterization is r equal to t squared I hat plus 2tj hat plus tk hat. So the derivative r prime would be 2t I hat plus 2j hat plus k hat. And so plugging into this formula that my integral f dot dr becomes integral f dot r prime. Oh gosh, whatever that is, I don't want it doing it. We haven't talked about the bounds yet, so I'll leave that alone. But my f was 4t cubed t to the 4th. And my r prime was 2t 2 1. I wrote these in angle bracket form because I think the I hat, j hat, k hat can make things look a little messy inside the integral. And so that's all stuff that depends on t. That's looking good. And I need to pull my bounds for t from what was given in the parameterization, 0 to 1. And then from here, I just have to evaluate things. So this dot product is going to give me 8t to the 4th plus 2t to the 4th plus 0 dt. So that's the integral from 0 to 1 of 10t to the 4th dt. Integrating t to the 4th is going to give me t to the 5th over 5. 10 staying there as a constant, evaluated from 0 to 1. But that's just going to be 2t to the 5th from 0 to 1, or 2 times 1 minus 2 times 0 is 2. And that's the exact same answer we got before. So both the approaches get you the right answer. Just the fundamental theorem tends to be a little bit easier because you don't have to parameterize a curve. But whichever you prefer will still get the right answer.